Hello, welcome to this lesson of the Linear Algebra Tutor. Here we're going to talk about the matrix adjoint and how that relates to the matrix inverse. We've spent quite a few sections talking about how to calculate the determinant of a matrix. We know several different ways now. Hopefully now you understand the big picture with the different ways that you can do that. And we're going to end up applying this to formulate something called an adjoint matrix. And then we'll use the adjoint to calculate the inverse of a matrix. Now, if you remember in Volume 1 of Linear Algebra, I actually already taught you how to calculate the inverse of a matrix, and we ended up using row reduction techniques. This is just an alternative way to calculate the inverse. You know, you're going to find that a lot in linear algebra and also in other math classes, is that you'll learn something and you'll understand how to calculate it and what it's for, and then later on, once you've learned more material, you'll come back around to those same topics and realize that you can calculate those same things various different ways. And that's all that we're doing here. We're using these concepts to basically help us calculate matrix inverse other than using row reduction techniques that we've learned. Okay, so let's first of all recap a little bit. We're going to use the same matrix that we've been using a lot because I think by using that you kind of get really familiar with the process. -1, 1, 2, 0, 6, 3, 4, 7, 5. We've used this a lot and we've looked at the submatrices, we've looked at the cofactors everywhere, and if you remember back, you can at every single point in this matrix define a cofactor at that location. For instance, if we're looking at the location here, we'll cross this row, cross that row, find the determinant of the submatrix that's left, and then it's going to either be minus or plus depending on the location and the pattern in the matrix. Similarly, we can find a cofactor here, and a cofactor here, and a cofactor here, and a cofactor here, and so forth. So what we can do is once we know all the cofactors of the matrix, we can define something that we call the adjoint matrix, which is something that you will definitely need to learn in your linear algebra course. And it is the transpose, which we've learned about quite a while ago, the idea of a transpose, of the cofactor elements. So I'm going to call that Cij. These are the cofactors everywhere in this matrix. Of course, they're called cofactors, so I'll put it here, of a matrix. And this is written as adjoint ADJ A, or adjoint B, or adjoint C, or whatever the name of your matrix is. You just put an ADJ in front, that means adjoint. So it looks, you know, a little bit cumbersome, these definitions, but it's a very, very simple idea. For instance, if we look at this matrix, we've actually calculated the cofactors of this several times since we've used it. So let me remind you, the cofactor for this position, when we calculated it before, we had a 9. The cofactor for the position over right here was 12. The cofactor in the position over here, what we calculated was -24. And we got these by taking the crossing out the row and the column, finding the determinant of the submatrix that's left over wherever we're at, and then either being minus or plus depending on the pattern that we had, which is -1 raised to the I plus j power. So it depends on the location where you are in the matrix if that coefficient's negative or positive. These are the first three. We've already calculated those. I'm going to write down the rest of them. C21, that's the cofactor in this location, is 9. C22 is -13. C23 is 11. And then finally here, here, and here, the three cofactors, C31 is -9, C32 is 3, and C33 is -6. All right, so basically what you can do is you can arrange these into a matrix. So before we jump into writing the transpose, I'm just going to say a symbol in matrix. And this very simply a matrix of numbers. Row 1, column 1, 2, 3, row 2, column 1, 2, 3, row 3, column 1, 2, 3. We just write the numbers 9, 12, -24, 9, -13, 11, -9, 3, and -6. I'm going to make sure all those are right before we continue. Those look right to me. Okay, this is just assembling the cofactors into a matrix. Okay, so what we do is we say that the adjoint, ADJ of matrix A, is simply the transpose of this matrix. So it's the transpose of the cofactors, you know, when we arrange them in a matrix. So the way you write a transpose down is you just take the rows and you make them columns. So the first row is 9, 12, negative 24. So we write 9, 12, negative 24. Whoops, negative 24. We go to the second row, 9, negative 13, 11. 9, negative 13, 11. And then the last row, negative 9, 3, negative 6. Negative 9, 3, negative 6. Let me make sure this is right. So this is 9, 9, negative 9, 12, negative 13, 3, negative 24, 11, negative 6. This is called the adjoint of matrix A. So on a test or a quiz or an exam or something, you might frequently be given a matrix, and it's just a very simple question. Write the adjoint of matrix A. So there's a couple steps to that process. First, you have to know what a cofactor is because you have to find all of them at every single location in the matrix, right? Then you assemble them directly as they sit into a matrix, and then you take the transpose of that matrix. This thing down here is called the adjoint of A. Don't forget to take the transpose. Some students assemble them in a matrix and say, this is your adjoint. It's not the adjoint until you take the transpose. Notice the definition says that the adjoint is the transpose of the Cij cofactors of a matrix, written as adjoint A. All right, so why are we defining something called an adjoint? Clearly, it's a great test question, something I can ask you, see if you know what you're talking about, but what's it used for? Well, there's a couple of very cool properties of adjoints that make them useful. Let me show you the first one right now. This is just a property. It's not something that you would ever be expected to just know, but it's something that once I show you what it is, you should be able to prove or show that it's true. Matrix A multiplied by adjoint of matrix A. So matrix A multiplied by its adjoint is going to be equal to the determinant of matrix A multiplied by an identity matrix. Multiplied by an identity matrix. I think you understand what the left-hand side means. Let me kind of circle this a little bit. The left-hand side means I take a matrix, in this case I have it written on the board, I find its adjoint, I wrote that on the board. If I multiply those things together, that's what the left-hand side is saying. On the right-hand side is saying, I have an identity matrix. Don't forget, what is that? That's a matrix full of zeros, except for the diagonal has ones everywhere, okay? And I'm multiplying this identity matrix times the determinant of A. So whatever this matrix is, whatever its determinant is going to be on the diagonals of the new matrix. That's what it basically means. On the right-hand side, when you have a number times an identity matrix, it means that this number is going to be always on the diagonals and zero everywhere else because this number is multiplied for every element of the matrix. And there's ones on the identity diagonal, zeros everywhere else. So if you remember, well, actually, I'm not going to spoil it for you. Let's just show ourselves that this is true. If we go here and write down this matrix, negative 1, 1, 2, 0, 6, 3, 4, 7, 5. This is matrix A. And we multiply by the adjoint of A, which we just wrote down, 9, 9, negative 9, 12, negative 3, 3, negative 24, 11, negative 6. So this is adjoint of A. So matrix times its adjoint. You're going to get something that basically says determinant along the diagonals. Well, if you actually get down with a calculator or with a pencil and paper, and you go across and then down, and across and then down, and across and then down, and this way and down, and this way and down, you basically go through all the multiplications. What you're going to get is negative 45, 0, 0, 0, negative 45, 0, 0, 0, negative 45. Basically, if you remember back from before, we've used this matrix a lot. The determinant of this matrix A is negative 45. So when you take the matrix, you multiply by its adjoint, you get a new matrix where the determinant lies along the diagonal and there's zeros everywhere else. Why do you care? It's a property. This is a property. It's a property involving adjoints. Adjoints are defined in terms of cofactors and things, and when you think about it, the cofactors involve determinants of the sub-matrices. So it kind of makes sense that when you multiply the matrix times its adjoint, the result might have something to do with the determinant of the matrix. That's basically what it is. So when would you use this? You can use it in proofs. You could use it in other situations, but also you just need to know it. I mean, just like distributive property in algebra. Sometimes you just have to know some of these things. All right. Now let me go and show you another property. This new property over here, I'm actually a little more excited about sharing with you. I think it's more useful. So this is a property of adjoints. If the determinant does not equal 0, which is most of the case, but you have to show that that's true, or you have to assume that that's true for the following, then the inverse of a matrix, okay, is equal to 1 over the determinant of the matrix times the adjoint of the matrix. This is extremely important. If you remember back from volume 1 of linear algebra, we talked about matrix inverse. We used it for lots of purposes. And I showed you how to find the inverse of a matrix, and the way we did it is by row reduction techniques, okay? This is showing us an alternative way to calculate the inverse of a matrix, which is useful in so many situations, but you don't have to do row operations. What you need to be able to do is find the determinant of the matrix, A, and you have to be able to find its adjoint. So in order to find its adjoint, we've been talking about it, you have to go and find all the cofactors and then arrange them in a matrix and then turn it on its side like a transpose. Whenever you take 1 over the determinant of the original matrix times its adjoint, you get a new matrix called the inverse matrix. And you should know by now, the inverse matrix is used all the time. So let's take a trip down memory lane and recall. When I first showed you the concept of an inverse matrix, I've covered it here in the last 2 lessons. I also covered it in volume 1 a long time ago. For 2 by 2 inverse, just like determinants are easy to calculate for 2 by 2s, inverses are easy to calculate. We said, and this is typically given like in a college algebra class, that the inverse of a 2 by 2 matrix is 1 over AD minus BC times this matrix, D, negative B, negative C, times A, right? Or I shouldn't say times A, D, negative B, negative C, A. And I hope that you can kind of see the similarity here. See, when you first start learning about inverses and the concept of matrices and the concept of equations, the concept of solving equations, it's a huge burden to go through cofactors and adjoints and all this stuff. It's too much stuff. So what we do is we say, hey, here's 2 by 2. Here's how to find the inverse. If you have a matrix where you have A, B, C, D, you find this quantity, and then you form a new matrix with the letters in there swapped around a little bit with negative signs. Do this multiplication. This is what we call an inverse. And then we show you through lots of examples what an inverse is actually useful for. All right, and then we go and show you for 3 by 3 matrices and larger how to find inverses, which involve row reduction techniques. Now we're circling back and we're saying, hey, this thing that you learned a long time ago from 2 by 2 matrix really is what this is. This is, let me go ahead and change color. This simple little formula that we learned a long time ago really is 1 over the determinant of A, because AD minus BC is the crisscross determinant of a 2 by 2 matrix. And then this thing here, this matrix here, believe it or not, is actually the adjoint of A. All right, I'm not going to prove it to you, but basically if you take any 2 by 2 matrix and you find all of the cofactors and then you put them in their place and you take the transpose, it's always going to turn out to look like this, D, B, C, A, and you have to have negatives on the diagonal. It's always going to be true. So because of that simplicity with the 2 by 2 system, we just tell you in the beginning to use this formula. We don't tell you where it comes from, we don't tell you why it's useful, but now you know it's 1 over the determinant of the matrix times the adjoint. Now the reason this is useful is because you can always use this for 2 by 2, sure, but now we have something more powerful that we can use to calculate inverses of 3 by 3 and higher order matrices, right? We wouldn't use this because this is only for 2 by 2, but for a higher dimensionality, we just have to know its determinant and its adjoint, boom, we're done. So let's take a minute to do a quick example just to show you how you might use that. And in fact, we have let's go back over here actually. We have a nice matrix already done. So let me go ahead and just kind of draw a little line here. All right, notice we have a matrix here, matrix A. We've been doing it all the time. We know its cofactors. We've put the cofactor matrix in place. We've taken the transpose and now we have the adjoint. We also know from doing this, right, and also from previously using this matrix, that the determinant of this matrix is negative 45. So if we wanted to find the inverse of this matrix, all we need to do is say 1 over the determinant of the matrix times the adjoint of the matrix. Now the determinant's negative 45, so 1 over negative 45, and then the adjoint, we now know what that is. In fact, this is the adjoint because we did it previously and we used it right here, so I'll just copy it. 9, 9, negative 9, 12, negative 3, 3, negative 24, 11, negative 6. That's the adjoint there. And let me switch colors. So the inverse matrix, it's a little bit cumbersome because you have a 45 as a fraction out here and you have numbers in there, but you can see that if you multiply this constant to every single position in the matrix, is what we do when we have a constant out in front, you get negative 1/5, negative 1/5, positive 1/5, negative 4/15, 13/45, negative 1/15, and then you have 8/15, negative 11/45, and then you have 2/15. And I'll extend my box down here. I'm gonna make sure that's right. Negative 1/5, negative 1/5, 1/5, negative 4/15, 13/45, negative 1/15, 8/15, negative 11/45, 2/15. So this is correct. This is the inverse matrix. So for some crazy reason, if you had a system of equations, you were solving it, and professor said, I want you to use inverses to solve this guy. Well, you can find the inverse of this matrix by row reduction techniques we've learned a long time ago, or you can just find its determinant and its adjoint. Which one's going to be easier? Depends on the matrix. I mean, there's really no right answer for that. It's just an alternative way. The same exact relation will hold for matrices of higher dimensionality, but as of now, you know that finding the determinant of higher order matrices and its adjoint is a little harder the larger and larger you have dimensionality in the matrix, because you have more and more terms that are involved. So the main point of this lesson is to introduce the concept of an adjoint. We write the cofactors down, take the transpose, that is the adjoint matrix. We verified that when you take a matrix times its adjoint, you get a new matrix that just has the determinant of A on its diagonal. And then finally we said that the relation we used a long time ago for a 2x2 matrix is really equal to this property that's very important, that the inverse of any matrix is 1 over its determinant times its adjoint. And we just verify this for you here, where we have 1 over the determinant times the adjoint, and you get a new matrix. Sometimes matrix inverses have fractions in them. You know, sometimes they look ugly, but that's just the way they are. Once you have this inverse, you can use it for any number of applications, solving systems of equations and other things out there as well. So the purpose of linear algebra is to give you tools. It's like a tool bag that hangs here. And so now you know how to find determinants multiple ways. Now you know how to find inverses multiple ways. Hopefully some of these properties are going to sink in. I'm going to show you a few more in a little bit, and then we're going to go and talk about linear independence, rank of a matrix, and things like that. We'll move on towards eigenvectors and eigenvalues.